Okay. In my case, my personal journey with program synthesis began from clinical problems. Began from this particular data set. It's called Mimic 3, and these days there is a newer version called Mimic 4, which is the biggest available to the scientific community data set of clinical data. Basically, it is a data set of clinical histories of patients in intensive care units. So when a patient gets admitted to a hospital with some severe condition, they record a history of events, and the kinds of events in this data set are the patient has been admitted, the patient has been discharged, the patient has received a certain drug, or the patient has undergone a certain surgery, and all of the measurements that were done, blood pressure, oxygen saturation, all of the results of the blood tests are also events in this data set. From this, we're interested in learning some techniques, this is a big data set, and there is enough data to learn something new about how healthcare should be done, right? We're interested to improve the way doctors treat these patients. And so you can view it using this model, using the simple formalism that the doctor is an agent, that it's sort of a reinforcement learning agent, right? That picks actions that are treatments and observes various measurements, vital signs. And it receives a positive reward if the patient goes home healthy, receives a negative reward if it takes a very long time to heal the patient, or if the patient dies. And we can also treat the patient this way. So if we are interested in creating a model of the patient, we can define a patient as an agent that observes treatments and outputs vital signs. And this leads directly into the standard reinforcement learning framework, right? This is the partially observable Markov decision process where the doctor is optimizing for the optimal reward. So the first thing we've tried is reinforcement learning. The first thing that obviously comes to mind is trying to imitate the doctors using the neural network. We have a data set of patient states and what the doctors did to these patients in these states. And you can learn a neural network that imitates the doctors pretty well. But we are not interested in just imitation, right? The imitation isn't that interesting if we have a huge data set and we can potentially figure out some way to treat patients better than they're treated currently. And for that, you can train a reinforcement learning network on a simulator. And one way, this is the work that we're going to be, this is the software we're going to be releasing, I think, early summer or late spring, which is VirtualS is an available simulator that it is used in nurse training. So it's a simulator that shows you, basically, it's a game that young nurses, medical personnel try when play to learn the important skills of their trade. So it was created by professionals in the field, and this game gives you valuable feedback of like everything you did wrong. And we turned it into a reinforcement learning environment, and we're going to be releasing it soon. And you can train, if you train a network on that, then you're actually optimizing for good behavior. for good results and not for imitation. Except you're not really. So you are optimizing for good results, but the simulator was created by a person. The simulator was created by a clinical specialist. So essentially, you're optimizing for the correct approach in the mind of that one author. So you're optimizing for the approach that they tried to teach you, for pleasing the teacher. And so we would like to optimize for the real good treatment. You would like to derive the simulator from the data. And we have done, there is an existing simulator that unfortunately doesn't work because there is a magical sequence of drugs that always heals any patient. It apparently overfit. We have also developed our own simulator that's, I guess, outside of scope of this talk, since we're focused on program synthesis, but it's this graph of states that is based on real states of the patients. Here, and with this kind of simulators, we were actually able to train neural networks that at least try to optimize real, like, high quality validation is a problem here because it's hard to validate something. No one would let you validate something on real patients, but it at least attempts to actually optimize for high quality treatment. And this is the crux of the problem now, is that no one will let you test a black box neural network on patients, and no one will let a doctor do something that's suggested by a black box system. Right? In healthcare, any decision system in healthcare has to provide explanation why it suggests you're doing what it suggests you to do. It has to be in some way transparent, so that the doctor can look at it and factor in their own opinion and see if they actually trust the assessment of the system. And here we came pretty naturally to program synthesis. If we can't publish a neural network and let hospitals use that, what if we try to learn clinical protocols? So if, as it turns out, a lot of healthcare is controlled by a program in a way, because there are these documents that are called clinical protocols that define. Oftentimes they're literally flowcharts. So there's a flowchart that defines what the doctor should do, how the doctor should go about assessing the patient when they came in, and then how the doctor should go about treatments. So this is actually an algorithm, and you can rewrite it in a language like Python and get a real program. And so what if we use the simulator to learn a better clinical protocol? So now instead of having a neural network that takes decisions, all of the clinical decisions are taken by a program, but we are interested in using machine learning to come up with a better program. And then our problem setup consists of three important parts. So there is a simulator, partially observable Markov decision process. This is an environment where you can easily play around and try out new strategies and gather how good they are. The second part is that we have a data set of what doctors did in all the situations. So we have a data set of decisions taken by experts, and we can imitate them. And we have a data set of experts' programs. So we can actually have a data set of programs that currently work in healthcare. And that is an optimal, I would argue that this is the kind of problem where program synthesis is most useful. Let me skip the slide. If you had just the environment and you would like to optimize for the environment, that is a reinforcement learning problem. And for now, program synthesis, like programmatically interpretable reinforcement learning, doesn't outperform black box reinforcement learning directly. So the best thing you can do is take a neural network, take some deep Q-learning algorithm and optimize that. If you just have a dataset of expert decisions, then you are looking at a supervised learning problem. So the only thing you can do, if you only have expert decisions, then the only thing you can do is imitate. And then it's a supervised learning problem. If you just have the expert programs, you have to use them, right? You have no way to come up with better programs. So you need to use a rule-based system based on these expert programs. But if you have all three, then this is a setup where I would argue program synthesis is actually the best solution. Because you can incorporate all three parts. With other approaches, you can't incorporate all the knowledge you have. You either throw out the programs, and this is important knowledge, or you throw out the data. So you would have to throw out part of the knowledge. And this is actually similar to the way people learn languages, right? When you learn a language, you can read theory books and learn grammar from grammar books, or you can try speaking the language and with trial and error learn how to speak it, or you can read a lot and learn by example. But anyone who has learned language successfully has probably used a combination of the three approaches. Doing it just with theory books or just with examples is usually a losing move. And the optimal, the brightest example of this problem. So we came to this formulation in healthcare with this healthcare simulator, doctors' decisions, and doctors and clinical protocols. But I think the brightest example of this setup of this task where program synthesis is optimal is competitive programming. In competitive programming, you have these websites that publish a task. They publish a task described in natural language, so it's described in English in this case. And it has examples attached to it. So they have input-output examples. And after the competition has finished, they also have collected all of the submissions. So you have a lot of examples of good programs. And so competitive programming is the ideal, you can think of it as an ideal data set for program synthesis experiments, and we're currently, Sander, who is with us here, is currently looking at those data sets, and generally we plan to, if anyone is interested, by the way, in trying to beat programming competitions with program synthesis, that's our plan for the following year, and feel free to send us an email. We can join forces, maybe. And then we have this setup, right? I have completely skipped for now how you actually go about creating these programs. So this is traditionally, this was done by genetic programming, where you would initialize a sample of programs and then randomly perturbate them, either take one program and apply some random mutations to it, or merge a couple of programs. And then you would delete the least successful programs so that over time your average programs are programs are better and better. Then the newer approaches deal with neural networks, and they have been largely inspired by because of the revolution that has happened in natural language with deep neural networks successfully modeling natural languages, there is now an interest in neural program generation with very similar models with LSTMs, for example, or transformers, to generate programming languages and to essentially backpropagate the reinforcement learning result through the neural network. So there are a couple of examples of papers that do this. I have also, this is a paper that I have recently published where we are using LSTM and genetic operator and genetic programming. So you have a database, code base of examples. You launch every program in the real environment, and you measure its fitness. You measure how well it performs in the environment it has to perform in, and then you can add new programs to the code base, either via an LSTM, and after the LSTM has added a new program and it has been tested, you can backpropagate through the LSTM the result, the measurement, the evaluation result. Or you can add them with traditional genetic operators. So you can take another program from the code base and shuffle the characters from there, for example. And what we showed there is that combining there was never a reason not to use both neural approaches and genetic approaches, and we show experimentally that a combination usually works better than one or another. It's probably because a neural network can approximate the space of good programs, but it can never approximate it well enough so that the optimal program, according to the neural network, is actually the optimal program. But what it can do is approximate it well enough so that the optimal programs are a couple of mutation steps away from what the neural network would produce. And so the combination of these approaches means that you learn this neural network that can produce decent programs, and optimal solutions are a couple of steps away. And genetic programming lets you take the steps. And the approach we're working on at the moment is what I call deep genetic programming. It's a similar approach where you have a population of programs, you evaluate them, evaluate their fitness, throw out the least fit ones. But instead of using a neural network that produces the program from scratch, or using some of these dumb mutations, what if the neural network was the mutator? So you can have a neural network that takes the program as an input and outputs a mutated version. And then you can actually start training a smart mutator. So if you backpropagate the result through the mutator, ideally your network should learn how to turn a program into a better program. That would be the hope. And then you just iteratively apply the smart mutations to the programs in your code base until the programs are good enough. Now, all of these approaches run into what I call the sparsity problem. It's the problem that most of the space of the programs that you can write is grammatically invalid. So if you generate some random piece of code in C++, chances are it just won't compile. This is the most probable thing that will happen. And so any kind of learning framework that you use to generate programs will have to deal with that, and will have to first learn how to produce valid programs at all. And only then it'll have to learn how to separate, how to produce programs that do what you need to do. And one approach to that is making programming languages that are so simple that you don't have any chance to screw up. So you don't have any possibility for a program not to compile. So there is this language that I have recently published that's based on BrainFark that turned out to be actually a good programming language for program synthesis, because it's very simple. It's based on a Turing machine, and we have added a few operators to make it more expressive, and also added a few fixes to make sure that there is literally no way for you to fail. So, for example, there was one way there for a program not to compile. It's when the square brackets don't match. And that was the only way for a program not to compile. But I added a module that if your square brackets don't match, it adds the necessary number of squared brackets in the beginning or in the end so that they always match. And then all of the time spent, all of the learning resources you spend are spent on solving the problems and not on learning the complexity of the programming language and on how to produce valid programs. And also, there's the problem that the loss function is really a really bad loss function, right? It's a loss function that's mostly zero, and so your gradient doesn't help. Another approach that I just cover for completeness, I haven't done anything related to that approach, is program synthesis by sketching. It's an approach where a human developer has to write a sketch for the program, and then the synthesis system only fills in the missing details. So the synthesis system fills in the parts that are designated as the part that have to be synthesized. And the sketch sort of takes away most of the opportunities to screw up and to produce a totally wrong problem or an invalid program. And you're only and also you can deal with inputs and outputs and things that are obvious, even if you don't know the correct solution to the problem. And this is also an existing and sort of working tested approach to sparsity problem. And the third one is language modeling. So if you have any kind of language model, the language model can tell you. So if you have a probabilistic language model, then this language model can tell you how likely is this program to be grammatically valid. And then you can use it in your loss function to produce grammatically valid programs. Or you can have a language model that's structured as an autoencoder. Then if the autoencoder is trained well enough, any random vector passed through the decoder should theoretically output a valid program. And if this is the case, then you can generate programs in this latent space and be sure that whatever goes through the decoder is a valid program. So this is also current work. There's CodeBird that trains a language model, and we are currently training an autoencoder system. And one more prior that you can apply here is that unlike in natural languages, so in natural languages, there have been a lot of attempts to represent sentences as trees, to parse them into trees and to handle them as trees, and they mostly have failed because the problem of parsing the sentence into a tree is a really, really complex problem. But in the programming language, actually the first thing your compiler does, or your interpreter does, when you feed your program into the compiler, is to turn it into a tree. And with the programming language, we have a definite way of transforming the program into the tree. And so the most, all of the, I think, state-of-the-art language models in programming languages typically operate in the space of this abstract syntax trees and not in the space of text. And so, for example, this work by Alon and others represents programs as trees and then predicts the missing node. So it's a language model that can predict a missing node in this tree by separating this tree into several sequences. So we know how to do sequence prediction. We're not sure how to do tree prediction. Right? With sequence prediction, we have been doing it with RNNs and LSTMs and all kinds of models for a long time. And so they decompose this tree into a lot of sequences. One sequence is the sequence from the root to the node. Another sequence is the sequence from a leaf to the node, and they have a sequence from each leaf to the node that you want to predict. And then they embed each of the sequences into a vector, and then they have a small neural network that combines all of the embeddings into the final prediction. And I would say this is currently probably a state-of-the-art in language modeling in source code. And obviously there are self-reported results, so take them with a grain of salt. But it looks I talked to the authors, read through the paper, looks trustworthy and really, really interesting. And then this gives you, having this autoencoder approach gives you a very easy opportunity to apply all of the operators. Right, you can apply the generator, generate the program in latent space. You can apply mutations in latent space or crossovers by averaging over two vectors in the latent space. And to get it back to healthcare, this lets us really this lets us do the full cycle of clinical protocol optimization. So you first, this is sort of the structure of my PhD. These are all the things you can do with program synthesis given a healthcare data set. So first you have these official protocols. You have the official algorithms that you have to operate. You need to translate them to machine language, and you can probably do it manually because there are not a lot of them. But technically, this is a problem of semantic parsing. So you can, it is also an interesting machine learning problem. If you have a lot of these protocols, how do you actually translate them from natural language to machine language? Then you use one of the approaches we've talked right now, or one of the approaches that exists that I haven't covered because I don't know everything definitely, to optimize for imitation. So based on this data set, it's very easy to create a simulator that will give you a reward based on how close you are to actual doctors. So you get a high reward if you do the same thing that the doctors did, and you get a low reward if it's different. And then you can optimize for imitation, and you can you end up with a program that that imitates doctors as closely as possible. And this is a very interesting research result in itself, because you get de facto protocols that might be really different from official protocols. Right? We know for a fact that oftentimes doctors have some knowledge, some domain knowledge that is not in the official documents. And the way they operate, especially, it's interesting to look at COVID data if we get our hands on it. Unfortunately, we haven't of now, because protocols for COVID have been created over a span of a couple of weeks, and then they have been updated very fast because nobody knew how to treat COVID. And so the hands-on knowledge must have been ahead of the official knowledge, right? So by parsing doctors' behavior this way, you get a distillation of what is the actual protocols that the doctors are using. And then you can create a simulator that actually tries to predict, based on data, what will happen to the patient after a certain action. And in this simulator, you can optimize not for imitation, but for health. And you can pre-train on all of those programs you have. So you can use you can initialize the code base, initialize the population with official protocols, with de facto protocols, and try to improve them, for example, with neural mutation. And this is my goal so this is my ongoing research, and this is my goal for the year. If any of you is working on something similar, it would be really interesting to join forces. And so, yeah, thank you for listening. I would now like to open myself to your criticism, roasting, and questions. Oh, yes. So there is this question in the chat. Alexander Skidov has tried doing. Yeah, we should definitely get in touch. So I have talked to the maintainer behind Code Forces about getting access to their database of tasks and submissions, and the maintainer mentioned that I'm the third, that we are the third team that approaches them with this problem, with this idea, and he said that two previous teams have mostly failed. So it would be nice to learn from their mistakes. Yeah. I should definitely look at what they tried and at least learn from their mistakes at the very least, and probably maybe get them on board.
I have a quick question about this. What
sure.
kind of, what will be your DSL for learning?
So there we would probably like to work directly with C++ or whatever language they're using. And there you definitely have to use something like autoencoders, because without that, that would never work. But my hope is that with a good enough autoencoder, you can generate programs in C++ directly. And if that doesn't work out, then we'll be looking at DSLs, definitely.
Oh, wow. Okay.
No, this is the reason why we're so interested in language modeling and in autoencoders, right? Yes, we would be interested ideally in using, in generating programs in industry-grade programming languages. I'll let you know how it goes.
Yeah, I have to say I'm a bit skeptical about the possibility of generating C++ code. I feel that your idea of using brainfuck, for instance, makes sense because at least every program is, or almost every program is syntactically correct and compiles and whatever. So it's much easier to generate. But even the question of generating syntactically correct programs in C++ that compile is non-trivial.
It's definitely non-trivial, but in this machine learning, so in the structural language models for source code, when you leave out a part of Java code and make it predict the program, it usually predicts a program that that compiles and that works. So I have hopes, although this is definitely an uncharted territory, and I definitely have backup plans for what we would do if that doesn't work out.
All right.
But I do feel like we have some recent advances. That means that maybe it wasn't possible like 5 years ago, and that would be possible today. So we have this models that leverage both abstract syntax trees, and they also leverage the deep language model. So in the structural language models of source code paper, they're using a transformer on top of these trees. And so we have had a technological leap that maybe will let us really generate programs in industry-grade programming languages. So at least we should try.
And in questions of motivation, why do you actually care to output C++ code? Wouldn't that be also fine to output something in your own, DSL?
But we are interested, for one, we are interested in readability, although readability of C++ is questionable as well. But the most important point here is being able to learn from C++ programs. Right, so program synthesis comes in as a very important approach when you have programs to learn from. You have both data and you have programs to learn from. And then you have to either learn how to work with this language, or you have to use a transpiler from this language to your DSL, which definitely is on my list of backup plans. But it's also non-trivial, and it has some additional problems of what if your transpiler doesn't work correctly, and what if your DSL is even less readable than C++. And then you have to, then you have to have a decent interpreter for the DSL and make sure that whatever you're trying to use these programs is compatible with that interpreter.
So actually, the Deep Coder paper's original motivation was to solve programming competitions. I don't know if you know about that paper. So, and they argued that, so granted, it was 4 years ago already, but they argued that they needed to design a DSL as opposed to use an existing programming language. But that was 4 years ago. So I'm taking your word that we've made progress there.
we've definitely made progress. It's not a sure thing, but I think this, and I have read that paper, so I will be taking their knowledge into account and trying to do better. But yeah, basically we are the next. We are the next attempt, right? So they tried to do it with 4-year-old technology, and they came to the conclusion that you have to have a DSL. And so with the progress we've made in 4 years, we are trying to make the next attempt at generating code in industry programming languages. Yeah, so anyone else wants to jump in? Or do you, Nathaniel, have any other points?